Hey guys, welcome back. Day 26. We're going to talk about intermolecular forces. All right, so intermolecular forces are between molecules, particles, ions, right there, in between, right? And so they are attractive forces, right? They're called van der Waals forces. And there are three types of these forces. So these are not bonds, all right? And we'll distinguish the difference. Because when, like, hydrogen is bonded to oxygen, that's an intramolecular bond, right? These are bonds between two, like, water molecules, or two molecules of sugar, or two molecules of propane, or two atoms of xenon, right? And so that's what we have here. And the first one is a dispersion force. All right, a lot of times we're referred to as London dispersion forces. All atoms and molecules have these London dispersion forces. They're what holds these atoms like together in the solid state. What holds xenon together, or what holds ice together, right? Right, or these intermolecular forces. Not necessarily dispersion force for ice, but right. These are what hold atoms and molecules together if they're nonpolar. So they depend upon the size of the molecule. Think about molar mass, how big the atom is, right? And so it's an attraction between a temporary dipole and an induced dipole on a neighboring molecule or atom. What does that mean? All right. Okay. Well, for example, if you have two atoms, I'm just going to duplicate that. I have two atoms, and they have their electrons going around. Color here. So we have an electron. Let's say there's an electron over here and an electron over here, and they're just both going around like in a circle. That's not exactly what they do, but let's pretend. Well, if, for example, both of the electrons are over here at one point, this side of the atom, of the first atom, let's call it atom A and B. The first side of atom A, the left side would be slightly positive, and this is slightly negative. That would be a temporary dipole, right? Because again, that's not even, it's barely even a fraction of a second. However, because it's slightly negative, that's going to influence, it'll influence the electrons over here, which will make these electrons want to repel, right, and go to the other side of B, all right? This is very short-lived. It's not very strong, especially in atoms and small things, but it exists. And so, for example, all right, if you notice, at the boiling point increases as we get bigger. So what happens is, as the molar mass increases, the boiling point increases. So as we get heavier, all we're doing is getting heavier. They're all nonpolar. You got hydrogen, you got methane, ethane, I drew a blank there, propane, butane, and the boiling point gets warmer and warmer and warmer. All right, now, there's actually three, this should be three, there's three isomers, not two isomers, three isomers of pentane. All right, and normal pentane would be C5H10 is a pentane. And so you'd have H, C, 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 C. Yep, H, and then they all have H's. And so that is your pentane. That's what it looks like. Right? A lot of times they call it N-pentane for normal pentane. The boiling point of this is 36 degrees Celsius. There's two more ways I could do this. I could take this, the end, and move this end to like that carbon and put this H, swap it. So if I did that, right? I would have 1, 2, 3, 4. And then I'd have, let's say down here, an A, C with the H's. All right. This would be, this is a pentane. There's 5 carbons, but it's technically 2-methyl butane. And its boiling point is 28 degrees Celsius. So what's the difference there? Besides 8 degrees Celsius and boiling point, there's something called more polarizability. So this is longer and thinner, so another one can stack and another one can stack, where the blue one here, 2-methylbutane, is shorter and fatter, so it's not as long. And so this one's more polarizable, right? Means that you can separate the charge more, okay? And we could even do it a third way, right? Which is called 2,2-dimethyl propane, where you have only 3 C's across, and then you have a C here with the H's, and a C down here with the H's, so it's still the same C5H10, except this has a boiling point of 9.5 degrees, and that's more of a compact ball. It's less polarizable, right? And so the more polarizable we are, the higher the boiling point, which means the stronger the intermolecular forces. All right, so that's what London dispersion forces are. So the heavier the atom is, the more London dispersion forces, or heavier the compound is, the more London dispersion forces we have. Okay. All right, the next interaction is dipole-dipole, polar molecules. All right, polar molecules. The molecule is polar, it has a dipole moment. And they tend to align themselves. What do I mean by that? Like just H to Cl, H to Cl, H to Cl, H to Cl, right? And then what's going to happen, something very simple, like just like this. Now, it's not perfectly arranged like this one's arranged, okay? They don't always do this. But if you kind of notice, right, for this molecule, this would be the negative side, this would be the positive side, right? And so we have all these interactions here. And the negatives and the positives are going to be, right, this is chlorine, that's a negative. But this H is positive, right? You guys, hopefully you see how it's kind of arranging themselves. Now it would be in 3 dimensions, but that organization causes the molecules to stick together more, which increases their melting and boiling points, right? So you can kind of tell how strong the intermolecular forces are on certain things based on their melting and boiling points, right? The higher the melting point and higher the boiling point, the hotter, the more intermolecular forces exist. And then there's something called hydrogen bonding. And this is a super strong dipole-dipole interaction, super strong dipole force. And the atoms are fluorine, oxygen, and nitrogen, right? So those 3 atoms can do this, right? And the hydrogen bond is between molecules. So if I have water here, let's just say, and another one over here, let's go with the hydrogen bond would be with this pair of electrons to that hydrogen, right? And so the hydrogen bond would be there, all right? And a lot of times we don't draw it like that. A lot of times we draw dots to represent that. All right? And so what's neat, water can actually make 2 hydrogen bonds, because it has 2 lone pairs, per water molecule, which makes water very unique. It's a liquid. It only weighs 18.02 grams per mole, but it's a liquid at room temperature, which is, we're very grateful for that. All right. And this is pretty neat because it actually holds together our base pairs in DNA. All right. So, for example, cytosine. Which a lot of times is C, right? This guy. So I'm going to try to draw this. C, 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 N, C, N. There's an O here, an H, an H, an N, an H, an H. All right. And we're bond everything. So there we go. And then another one. I actually have to move this over. Go. Guanine. Sometimes G. All right. And so this is C5H5N5O, where cytosine is C4H5N3O. All right. And this one, I'll try to get it correctly. There's O, C, N, C, C, N, C, N, H, H, and then we get another N over here, C, N, I think that's everything, oh, and an H. All right, so this one, I got H's here and here. It's a lone pair. All right. So the hydrogen bonds that we'll highlight, I'll just highlight these in green, are right here, and right there. So those are the 3 hydrogen bonds between those 2 molecules. All right. Now these actually change a little bit when they make what we call a polymer, right? When they get linked together, right? And so some of the H's come off and it looks different. But for right now, that's 3 hydrogen bonds help keep these 2 molecules together, which is kind of neat. I think it's fascinating. All right, so many properties depend on these intermolecular forces. And what we need to know is, does it hydrogen bond? So is it small? And does it have a nitrogen, right? As you can see, nitrogen or oxygen with a lone pair. You see how they have lone pairs, right? This oxygen has a lone pair with this hydrogen on a nitrogen with this guy right here, the nitrogen. So are they hydrogen bonding? Are they polar? Or are they not polar? So those properties, and those properties depend on, right, like they influence the melting point, the boiling point, how much energy it takes to vaporize, how they flow, right? What their surface tension is like, how, like, can you do a belly smacker into it, right? How much vaporizes, and then does it go up? Right? Does it go up a capillary tube, right? Like water will flow up a capillary tube, whereas not everything does. And then there's kind of a fourth interaction that's not intermolecular forces. Ions and dipoles, right? These actually are very important for like making solutions of water, are aqueous solutions. Okay, it contributes to why some of the salts dissolve in water. So what do we need to take away from intermolecular forces? Because that's the question, right? What do we need to take away? Well, we need to take away that if it's polar or not, and then does a hydrogen bond or not, and that's pretty much it for right now. Now, there are properties that will arise based on the intermolecular forces, especially in Chem 2, that we're going to dive into, all right, that we need to know. But other than that, right now, that's about it, all right? Hopefully that works. Thanks, guys. We'll see you next time. Let me know if you have any questions. Take care.